So we're still in one-dimensional data. We'll be on one-dimensional data this week and next. And one of the most important things that you do in any sort of data analysis is compare things. So we're going to move this up to start moving towards two-dimensional, but looking at comparing distributions and visual comparisons that we might make between distributions or between elements of those distributions, and think about which ways are better than others for making those comparisons. Okay? So here's a classic data set that's been around, or it's been in existence for a little over 100 years. And you all recall the Titanic, which sunk in 1912 off the coast of Newfoundland. We have data here on all of the passengers, or all the people that are on board. And the information that we have on is what class they were in. Were they first, second, or third class passengers, or were they a member of the crew? The sex of that person, male, female, whether they're an adult or child, and whether they survived or did not survive. So this is a table. We want to look at just comparing some of the numbers in this table. So the first thing you might think about is class. We look at the class of the people and how many people of each particular class survived or died. So you're working on this sort of stuff in your assignment now, so just getting margins of this table from the Titanic. I'm interested in keeping 4 who survived and what class they're from 1. So the margin that I'm doing the summations over, I want to keep that and sum over all the other indices are the 4th and the 1st. That said, I want to look at what proportion in each class survived. And so this little calculation here will give us these proportions, and there's the table of the proportions of survivors in each class. And that's a lot of significant digits, and they're organized horizontally. We know we can do a lot better than that. So just following the simple rules of table analysis that we have from Ehrenberg. So I'm going to round them, multiply by 100, so I have no decimal places. So I'm down to 2 digits. Then I'm going to change the orientation from rows to columns because it's easier to compare numbers. Arrange them in descending order, although that wasn't necessary because as you see it goes in the same order that they appear, first, second, third, and then print it. So here you can see immediately the differences, and of the percent that survived, those that were in first class passengers, 62% of them survived, compared to second class, 41%, third class, 25%, and crew, 24% of them survived. So you might imagine that survival immediately depended on which class of passenger you were. Okay, so that's an interesting thing. It's easy to compare those 4 numbers in a very straightforward way. When I think about how you might compare them visually, well, we could use the same data and think about using this length, right, of each of these blocks. So that's the, excuse me, those are the proportions of people that survive in first class, in second class, third class, and the crew. Right, so now we're looking at, I've just color-coded them and labeled them, but we're looking at comparing lengths along a common but non-aligned scale. Right? We can put them on a common and aligned scale, again using a bar plot. So what I'm using is these are both examples of bar plots with various of the options selected, various of the arguments set to values that give me the output that I would like. So now I've got this much easier comparison because they're on a common aligned scale. This is a lot like that, just the display of the numbers themselves. So you immediately see the proportion that survive in first class is much, much larger, right? More than twice the size, nearly 3 times the size of the proportion that survive in third or in the crew. Okay? Very simple, just using length. Those are bar plots. We could look at those that survive and those that don't survive in the same plot. And again, these are bar plots, a little work in getting the survival proportions, but getting the bar plot and adding a legend. And so Those that do not survive, the proportion are in dark gray. You see the crew, lots do not survive. And much smaller proportion of the first class do not survive. And conversely, since these have to sum to the same length, it increases in the number that do survive as a proportion. So that's telling you a little bit about the story about the Titanic and what your chances of survival were, at least for whatever reason, associated with class. And there are lots of reasons that you might imagine might be associated with class. Okay? So this allows you at once to see both the sort of distribution now of those that do not survive in the dark gray, and also those that survive in the that do survive in the light gray. Again, we could do a little better than that. Since we know it adds to 1, we could just show the proportions, and now you can see immediately that distribution. So if you look back here, if I'm connecting the dark gray lines, there's a lot of, if that's what I'm comparing, there's a lot of space. We want to remove that visual space between these dark gray lines, and that's one way to achieve it. I can see immediately at once the bar plot for those that do not survive and the bar plot for the proportion that do survive. And again, you can see just by the difference in the lengths of these various regions that there's quite a difference between third class and crew compared to either first or second class. Okay? And so this is also related to that effective framing, right? So back to Stevens's law, or the Weber law, the Weber-Fechner law, we're looking at proportions, right? So you can tell the differences here. It may be easier to tell the difference between these light guys than these dark guys, just because it's as large, the difference is a larger proportion. Okay? So those are bar plots. Well, that's just a couple of them, right? So what we're looking at, we're thinking of comparing these numbers, right, these proportions across a second variable, these different classes. So 4 of them here, and we can see the pattern in the distributions of each of these bar plots. You could do that for lots and lots, but you have to be a little careful about stacking up plots like this. So here's an example that I've taken off the internet somewhere on this trixietracker.com. We're looking at you can track the activity of your newborn, their sleep patterns, to see what's going on. So the yellow is they're awake, so this is Thursday, all right, November 17th. It looks like they're asleep, slightly awake there for a brief period, asleep, awake, asleep, awake, asleep, awake, etc. So you start to look, that's what happens on that day. Here's what happened the day before, right? So you look at time and see what are the sleep patterns of your newborn if you're actually interested in tracking that kind of information. The problem happens is when I don't know if you look at that already, it looks a little bit off, maybe not so bad on the big screen. But if I have a lot of these days, I line them up. So if I line up several days there, a little more than a week, I've got 10 days there. You can see that, I hope you can see, that it looks a little bit higgly-piggly, like it's sort of crooked. These lines are moving up and down, right? Which they're not. They're entirely horizontal. That's your visual system that's making that variation. Everybody see that? Anyone not see that? Do all of these horizontal lines look straight to everyone? To anyone? How about this? Are you seeing any motion, any crookedness of the lines? Okay, so that's your visual system. All those lines are perfectly horizontal. Okay, so you start stacking them up, you can produce some really bad graphics like this website has. Okay, you don't want to be doing that. So that's a warning. That's actually a well-known optical illusion. Maybe you can see it here. Even when I've got the same size rectangles, all of those lines that are going left to right or across the screen are in fact horizontal. But they look like they're on different angles. Okay, again, that's your visual system. You need to be aware that that's an illusion. It's called the cafe wall illusion after some cafe in Bristol, England. And there's the cafe and the tiling that they did, which these are all straight tiles, but they look like they're kind of wedge-shaped in some places. Again, that's entirely you constructing that. Okay? So be aware of what seems like a good idea for a few small numbers of things can actually perform very badly. This graphic back here, I discovered that some 3 or 4 years ago. It's still there. I mean, so it's not a good idea. So you may see this pop up in lots of different places. Okay, so if I look at just numbers, so when we're looking at bar plots, I can have them arranged vertically as well as horizontally. We can see differences easily between, here it's the actual number of passengers. So this is the total number of passengers in each of these groups. So I can easily see that there are tons and tons of crew, more third class, a lot of first class, at least the smallest group is second class. But I can see that dropping down from right to left, although in principle there is an order here that this is kind of ordinal, we can imagine, based on social status or the cost there of the ticket. If I look at those who died, that looks kind of the same shape, in the sense that crew's big, then the third class, and then these guys are two small ones. Not quite the same, but it's a little hard to tell because the differences are hard to tell because it's on a different page, right? So if I move that back, if I go back and forth like that, you might be able to tell easily by what's moving there, the different shape. But it's how much memory you have in the transition between one image and the other to see whether or not you'll notice that difference. The number who survive in each class actually looks quite different from the previous things. And in fact, if I were to present that to you, without telling you how many people there were, you might think, well, that's not so bad, right? Lots of people are surviving in the crew. In fact, it looks like a little more like the crew members are surviving than those in first class, until, of course, you know how many die. Okay, so that's simple bar plots. And then these things are fairly straightforward and fairly powerful. You can arrange everything that you've seen so far has been arrangement using the function bar plot on tables. Okay. If I frame this and I show you both at once, now I'm giving predominance to those that died, right? Because they're the bottom thing. Those that died are on the common aligned scale. Those that survived are on a common non-aligned scale. So I'm using this language again and again because I expect to be using it in this week's assignment of what we're actually noticing the difference between. So it's much easier to compare the size of the differences between the dark gray than it is the light gray. But that tells both of them at the same time. Now that's almost kind of two-dimensional data, right? So I've got one variable that's the survival, non-survival, and another variable that's the crew. So I've just switched up to a little bit of two-dimensional data. If I produce a bar plot to ensure that they're on a common scale, I'm going to have to make sure the y limits are identical for each one of these. But I'll do all three of these now. And those comparisons are on the common scale, and it's much easier to compare the differences between them. Again, the dead and the counts look roughly about the same, but we know that the proportions are different. Okay? And those differences are easier to tell when we frame them. And I guess, again, we've got position, length, and area because they all have the same width. So you've got sort of three ways of encoding the same information, so there's lots of redundancy there. So that's encoding individual, but I want you to think about the shape of that distribution. So I've got tall guys on the right and short guys on the left in both of these cases, and something a little different there. If I put them on without a common scale, now I don't care so much about the counts. I really am forcing you to think about the shapes of those distributions. These axes don't matter so much. I'm interested in, is the shape the same between the blue and the dark gray, between the dark gray and the light gray? etc. And you could definitely say that the light blue and the dark gray seem more alike than do the light gray to any of the other two. Okay? So when I have different scaling, when I allow it to find its natural scale there, I'm not paying any attention to the numbers, but I am sort of still thinking about the shape. Okay? So for example, the fact that I have more surviving a higher bar here in first class than I do in total doesn't matter. I'm interested in the shape. I've lost that information. So let's move on to a more interesting data set. So that's just categorical data, just looking at bar plots. I've taken this data set from the Elementary Statistical Learning package in R. This is South African heart data. And what we have is a bunch of individuals from a high-risk region of the Western Cape in South Africa. 462 cases, 10 variants are measured. And what I'm going to be looking at is just this one, systolic blood pressure. Okay, so this is the systolic blood pressure. That's the one variant that I'm interested in. And I'm going to want to do comparison in the distribution of the systolic blood pressure between two groups. Systolic blood pressure is a measure of the pressure that your blood's exerting on your circulatory system in the various blood vessels that you have. And then I'm going to be interested in whether you have a family history of heart disease. So we know whether the people have a family history or they do not. So that's a binary variant. That's a continuous variant. Okay, so there's only going to be two groups, those that have a family history and those that do not. So I'm just going to extract some each of these two groups. So simply find those who have no family history of heart disease, give that into one vector, which there are 270 people in this data set that have no family history. And similarly, those that do have a family history, set those aside, and there are 192 of those. So now we're going to compare the distribution of systolic blood pressure for these two groups of patients. So how might we do that? A number of ways. So we could look at box plots. So I'm going to look at the box plot of family history, of systolic blood pressure for those with and without family history. For the record, make a mental note of this. I'm going to use two different colors so you can tell which is which. The idea here is that red, the pink, that's good. Blue, that's not good. Okay? So if you have family history, you get light blue. If you don't, you get a light pink. So there are the box plots. So it's of interest, what's the difference between these two distributions? Anybody quickly? Yeah? Skews to the right, so both of these are skewed to the right? Each one? Yes? Or which one are you talking about? That this one does more? Okay, so that, and you're saying that because? Yeah, so largely in this box, right? 25% of the data is sitting there. That's much longer, so the center part is pulled out a little more. This one's certainly got some outliers out here. It does look more symmetric. This tail is, of course, still longer than that tail there. So there's still some skewness there, although it seems a little more dramatic in this one, right? In that the middle 50% of the data extend farther. Anything else? Well, one of them has lower systolic blood pressure generally than the other, although they roughly have the same range. You see here 100 to 220, 100 to 20, but I caution that they're not exactly on the same scales. So these are not common. Well, I guess they're common numerically, but they're not common visually scale, and they're certainly not aligned. So if you look at the numbers, those that have no family history seem to have the median, at least, over here somewhat lower. The bulk of the data, this box seems slightly to the left of this blue box, and cautioning again whether those 120s line up. So what you really like to do is line those up. So that's two separate box plots. It's simple to put them on the same box plot, and here we're using R's formula to explain it. So I've got a data set that's the SA heart, and I want to model systolic blood pressure as a function of this factor called family history. So that model knows that it's got two different factors, and we'll draw the appropriate box plot. So you may have seen this in linear models, LM of this. It's the same kind of modeling language that's being used, and we can tell that instead of doing a fit, this is the fitted model, right? These are the box plot values. And so it's a little easier to see the comparison, that the pink one is just ever so slightly in the middle part of the data to the left of the blue one. You can do that in ggplot as well. Just to have this for completion here. So the idea is you've got your plot, you've got your geometry that you're doing, which is a box plot. The aesthetics here, you've got two variables, an x and a y, which are, one is the response to the systolic blood pressure, the other is the category. And that would normally put that vertically. I want it to be horizontally just to fit on the slide and to match the other ones. The other ones, you notice that I've got horizontal equals true. In the ggplot, because it's a pipeline of transformations, I'm going to, after I've got the plot and I've applied the geometry to it, I'm going to flip the coordinates. So again, it's a pipeline of stuff. So same picture, slightly different aesthetics in drawing the box plot. The whiskers here at the end are not drawn on, but otherwise it's identical. Okay. So we might think about histograms. So what might you miss in that box plot? Remember, box plot is a model. It's got a model in mind, and one of the important features in that model is that it has a single mode. Yeah, so you're missing multimodality for sure. So if, for example, the reason that this thing is stretched out is that it's got a few modes in there, we've lost that. So going to histograms, again, the scale is not identical. And you see that they both look kind of skewed, right? There may, in fact, be more of a bump over here, and I start to think about, if I'm comparing these two and I'm thinking about family history on systolic blood pressure, is this a change? Is this shifting from no family history to a family history? Or these folks have slightly different distribution? And again, that's a little hard because they're not on identical or aligned scales. And so we might put them on a common aligned scale in both x and y. Right, so which is why I've got a fixed limit on the y in each one. And now I can compare them. I can see the vertical scale is identical. That's not aligned, it's common, it's not aligned. This is common and aligned, so it's easier to make comparisons in the horizontal direction. And I can also see the shape. Again, this is a little more smooth, maybe with a little bump down here, but we know there are problems with histograms depending on how I chose the bin boundaries, where the breaks are, etc. And again, this one maybe goes up there, I don't know, and more bumps there. So we might want to do better than that to be able to compare them. Again, I've used densities here, sorry, I have not used density, I've used frequencies here, so that you can see the relative numbers. There are more in this pink group than there are in the blue group, so you still have that information. Just the area of that whole pink thing is larger than the area of that whole blue thing. There are more people here with no family history than there are with family history. So what might I also do? I might put them, so I have common aligned scales vertically and horizontally. I may just put them on top of each other. And so you see that I draw one histogram, and then the other one, I add it to the existing histogram. And the colors I chose had alpha transparencies, so they should sum. So when I do that, it looks kind of like that. You see that the blue histogram is smaller than the pink histogram, so it's fitting mainly underneath, but it has its mode here roughly in the same place. And then it gets a little larger in this spot, and larger here and smaller there. So you can see the slight differences. That allows you, if you're looking at frequency, of course, if you're looking at shape, we should have probably imagined the densities, right? Use the density scale rather than a frequency scale. Okay? So one of the problems is it's a little hard to see what's going on there. This overlay, it's kind of cute that you can do this, but they're not on the same density scale, so the ones that have smaller numbers are going to appear there beneath the ones that have larger numbers. And secondly, I'm probably drawn to this purple, which is where they both agree. So I may in fact be thinking more about the shape of that purple thing, which is not really anything that meaningful. So I would argue this is probably not a very good representation of comparing these two distributions, even though I've got common aligned scales on both of these things. Even where there's a density scale, it still is lacking a little something because of the overlap. Okay? So what else might I do? So let's see, I can do the well, let's just see what we got here. I'm going to pick up the histograms and put them back to back. So that complicated code that we saw beforehand, what it's trying to do is just produce one histogram and the other one back to back. So now you have both of them there. You're looking at the shape. You can see roughly that there are more pink ones than there are blue ones, again by that area. So the bulk of the patients do not have the history. And you can also see relative shape of this histogram, the skewness, even though it's upside down. And you compare it there. These lengths comparisons, they're at least a common but non-aligned scale. Okay? So that may be a kind of a weird thing. You're looking at it. If it was identical, it'd be reflection in the lake sort of thing. You're seeing the actual same histogram. That's, anybody seen those before? Have you drawn those? Not surprised, right? This is a little complicated. So one of the things here now to go back and note is that I've chosen not to plot these as I did before when we were making the average shifted histogram. I've got the histogram objects in both cases, and I get the values, the counts there, and then I plot one. I have to flip things upside down, one of them upside down. So there's a little work here just flipping one upside down. Okay, so I plot the first histogram in the right scale, and then the second one I plot with the lines. So there we go. So if we have that and we're thinking about that, this has almost become a shape. It's sort of the shape is bulging somewhere around the middle here, and then it tails off on either side. The blue one is a little smaller than the pink one. And I could orient that in any way if I'm thinking that as a complete shape. So, for example, I could put these back to back. So a little more work, a little more code there to make it back to back. But I can put two histograms back to back, and now I've got this shape that I can see. Again, the same thing, the shape of the frequencies and without family history and those with family history, and see where they agree and where they disagree most, right? Disagreeing most in this spot right here. Okay, so there's another graphic. And now I think about, well, that's kind of an interesting shape. I wonder if another group of patients had the same shape, right, from some other part of the world. Is that going to have the same shape? Are they, if I grab roughly that same number, 462, whatever it was, of folks, are they going to distribute themselves in this way? Or are they going to be different some other way? So now this thing itself is doing a lot of work. What this is doing, it's going to give me those comparisons between the two sides. It's telling me the magnitude of the two groups, but it's also maybe defining this group of South African heart patients. And people use this kind of graphic to make those kinds of comparisons. And one that you'll see a lot is this population pyramid. So this again is just a histogram. This is Canada 2014. The bins are the age, right? So the age of different groups, and then how many millions of people there are in each, with blue naturally being male, pink being female. That's not natural, that's entirely a cultural construction. Okay? And so you can already see something, thinking about the distribution here. There's a tailing off here, as you might imagine. There should be fewer people in older categories, very few people up around 100. But there's this mode that's roughly around in the range, from, let's say, from 45 to 60, around in this range in the mode, and that seems to be mode on both sides where there's a bump. It almost looks like a muffin, right? A pointed muffin that comes in, and then it gets smaller again, and then the number of people in this lower group is quite small. So you might think about, as that moves through, the population of Canada is going to look a little different, perhaps. The other thing you notice is what's the difference between males and females. And females might be, there might be more females in some categories than others. Certainly on the top end, you see more females because women live longer than do men. At the bottom, you'd expect to see roughly the same. Looks like there's slightly more boys than girls here, right? Looking at point 8, this one a little bit farther away. So that's called a population pyramid. Yeah? What, in self-defense? Yeah, well, I mean, you can divide it in a lot of different ways to see. These are sort of grouped entirely just by age and sex. But you can imagine, like any population, you can take other measurements, divide it different ways. So these are back-to-back histograms, a population pyramid. Demographers like to look at this. And what's interesting is looking at different countries. So I'm going to point out, first of all, that this goes from up to 2 million on either side, which is identical to the Canadian one. Okay, so now we look at Canada versus Saudi Arabia. And Saudi Arabia does have this bulge, but it's much younger, and it does go in. So the bulge is around the 30s, 20s and 30s, and tails off, and not so many up in this high age group. Probably lower life expectancy in Saudi Arabia. Again, there seems slightly lower numbers of females than males, not so much, similar as it was in Canada, but a different demographic. And Canada's is not unusual in terms of Western developed nations. Not too unusual. There's slight variations. It gets more interesting now for other countries. We're not going to keep these the same, but you can do the same sort of thing. There's Iran with this bulge again around the 20s and 30s and tailing off. Maybe that's not that. Maybe it's more like Saudi Arabia than it is like Canada, right? Bahrain. I don't know what they're doing to their women in Bahrain, but this is definitely much smaller on this side than the males on that side. So the shapes are a little different. Bulges again roughly in the 30s, late 20s, early 30s. Uganda. The tragedy of Africa, right? I mean, we've got just massive amounts of children, large numbers here, and just tailing off. So this very different, that's indicative there's something very different in that society than what we've seen in the previous ones, right? China, of course, these numbers are much larger, 65 million on either side. Any one of these, there are more. See, that's frightening, right? There are more boys 5 to 9 years old than there are people in Canada. More girls 5 to 9 as well. So you can see, you expect to see some sort of symmetry in the sexes. in India. Again, a little low on the female side, it seems. It's not quite symmetric there, male to female, but it has that shape of a broad base and tapering up. Maybe slightly straightening up here at the bottom. Pakistan, similar sort of thing. Again, you see the straightening up at the bottom. And it gives you, now, these comparisons between distributions actually have become shapes to think about how you might compare countries. And you can look at lots of different countries in this way, just in their population demographics and a way of thinking about what's going on in the future. And there's Canada here. Another one that's sort of roughly the same shape is this one here, which is Italy. I think another Western country. And you can see some of these countries are more shaped this muffin shape than others, or reasons you can imagine related to birth control and other things. So those are back-to-back histograms. You have a question? Okay, so there are a variety of reasons. Why are there so many young people, right? Maybe because there's some economic benefit to have lots of young people. Maybe, in some cases, if you think of the AIDS epidemic in Africa, lots of adults being wiped out, right? War, conflict that was going to wipe out particular age groups. So the question is, people usually reproduce more during wartime? Right. So there are lots of sociological reasons that you can imagine that would change these. I don't know enough about these particular countries to say anything, particularly if I'm videotaping this. But it's, I mean, you think about the First World War, right, where there are millions of let's call it reproductive age men wiped out. That had a serious effect on demographics of anybody that was involved in that war, and there was a lot of countries involved in that war. So yeah, certainly conflict is going to have its effect, as will any epidemic, famine, etc. That's going to have an effect. And culture itself will also have an effect. You know, that's largely effect in Western democracies with the introduction of birth control. So that, you know, I come from a family of 6 kids, right? You don't see those anymore, right? So just to get something that looks, you're thinking about Canada, you know, being a classic case of Western democracy. If you looked entirely at First Nations, that looks maybe a little more like things we've seen in other less developed places in the world. So when you break it down by another population, there's also this, lots of young children moving up like this. They're not quite following the same demographics as the rest of the country. So I just want to show you that there are actually examples of back-to-back histograms, and they're useful for identifying. Now they become an individual visualization of a lot of things. There's a lot of information in that one visualization. And so they become one little component of making a grander visualization. One of the attractive things I mentioned last day about ggplot 2 is that this notion of a facet. So I have a plot. I have this mapping of the systolic blood pressure. I want these histogram to be white, and I want a facet grid. That is, I want you to break this up, whatever I've given you there, based on family history. Okay? And that immediately produces that. So it's arranged that these two plots be on a common aligned scale on this axis, and apparently on this axis as well with the counts. So what we went through some trouble to get, you get automatically just by saying I want these facets. And that's where family history is absent and family history is present. So that would be our pink and blue. So it's easy to do in ggplot 2 and produces some very aesthetically pleasing graphics. So what about density estimates? Well, I mean, why stick with histograms? So we could do density estimates as well. And the function that's going to do that for you is the density function in R. So this is going to do a kernel density estimate, And I'm going to use this method for finding the bandwidth. Okay, and so I'm going to plot the density. The funny thing with the densities, it plots just the curve, so I need to fill underneath it with a polygon. Okay, so there are the two densities. So now I've got a better sense of the shapes of these things without relying so much on the bins of the histogram. So again, I see the skewness, a little bump on the end, skewness, a bump on the end, and also there's maybe a bump here in the middle, which we would not see in a box plot, for example. Again, common aligned scales here. We could do the same sort of thing we did with box plots. And we could overlay them. So even with a density, so they're on density scales now. So I've lost these difference in size. It's still kind of hard because my mind might kind of attract to that purple, the combination of the two. It's not exactly a good graphic for this. So even though it looks nice to overlay, it's certainly I can identify where there are differences, and it's good for that to see this big difference in blue here and a big difference in red there. So it's moved slightly to the one side, but that purple shape is a little distracting. Reflect those in the same way, which means I can also put them back to back. So now I've got another shape that I can look at. I can talk about both sides. So I've lost the because it's density. I've lost the numbers of each. Remember, the number of pink is much larger than the number of blue. So I'm really just looking at shapes. So I'm looking at the shapes of this density estimate, and that bump there is showing that this lack of symmetry. It's almost like looking at a face. I mean, I think it looks kind of like the Grinch, right? If that was all green, that sort of looks like the Grinch's face, and you can see that there's this asymmetry that we spot very easily in faces, right? So you can see that asymmetry on a vertical line because so much of what we encounter socially is symmetric along a vertical line. So that's, you can see the differences there fairly easily, that it's not symmetric and where it's not symmetric. Again, with facets. The point is there are lots and lots of ways to present two distributions, one against another, that you might be able to tell the differences between them, and some of these might be better than others. We've done some fancy stuff, right? Box plots, histograms, and density estimates, but you could just do that. So I'm just doing a scatter plot of these points, those with no family history and those with family history. And I've used a transparency, so the density here is given by how deep the color is. So it's very light color, there's only one point there. When 2 points, you see that there's an intersection and it's darker. And then there's a lot of points here and there. Now, when there's so many, it's hard to tell. So a simple thing to do is just, let's move these points off of this line. Let's jitter them. Okay, so we're just going to jitter the vertical direction. So even that, without anything as fancy as a kernel density estimate, gives you some sense of how much alike these guys are. And you can see this lack of density in this region here, that second bump coming up on the blues. And the blues looks shifted slightly to the right in this middle part here. But there's not a big difference between them, right? So even something as simple as that. And sometimes that's the best thing that you want to have depending on where you're using the graphic. Yes? Pardon me? The question is it sort of overplotted? No, it is overplotted. So yeah, it's overplotted, and particularly that one's overplotted. And if those were all solids, I wouldn't be able to tell that there are more here than here. And so that's the reason for using this alpha transparency, because it sums. In fact, it looks like there are two there, right? Because that's a little darker than that one, I think. And so you're adding up. So the overplotting here, by using that transparency, you're still getting some sense of how many there are. I'm slightly moving the overplotting a bit by just adding some random uniform noise here. So if we go back here, present p-points. Oh, so I'm not randomly doing it. I'm just looking at what their order is in some value. Okay, just ordering. Oops. No, I take that back. I went the wrong direction. Phew. So I've got a random uniform around the value there that's producing the vertical scale. So that's just this random noise here that I don't care about, just to spread them out. Okay. So what we can look at are another way is looking at quantile plots, just looking at the quantile function itself, and do that for each one of them. And there's no family history, there's family history. And you can see again this sort of skewness going up, that tail being pulled up. This is also skewed, being pulled up here, but it kind of hits that skewness faster that we saw in the box plot. That's that bump that's going up here. There's the bump around here, that flat area. So you can interpret that easily, and we can put them on the common aligned scales. So those are the two quantile functions. So when you look at this, you can look at the pink one. You can see how much they agree. They do look a lot alike, this distribution, right? There's some disagreement in this area up in the 80% part. And you can tell that they seem to have very close to the same location, right? The median's about the same. We saw that before. Roughly the same spread in the middle, although it starts to fall apart here. So I think even compared to the previous plots, this QQ plot, this is not QQ plot, this quantile plot showing two different quantiles is allowing you to actually see the similarities, differences, and also read off some values. So I want you to get familiar with interpreting this kind of plot because it seems to be a very easy way to produce things on the same aligned scale, be able to tell different things. A little harder maybe than that for an icon, right? Because that's, again, some similarity, but it's got a lot of information here that you can tell fairly immediately and read off summary statistics to compare either. So I ask you to think about how do these actually compare in location, scale, modality, and how their tails compare. But those two groups look a fair bit alike. Any questions on this? All right, so that's a quick run through. What I want to do is compare distributions, and think that there are lots of different ways to compare distribution. Are some better than others? How could you tell whether one was better than another? Is there some way that we can actually assess how good any of these comparisons are? And we'll start to talk about that next day. So office hours now. If you have questions about the assignment, etc., go see me in M3.